Welcome to a lesson with Dr. Powell. Let's talk about a way that we can picture a right inverse of a linear transformation. Suppose that we have a linear transformation map F from R3 to some vector space V. And suppose that it's surjective. Now, if it's surjective, that means it has a right inverse. What is a right inverse? Well, um, if we think about it this way, we could actually think, okay, if we have a map or a function that goes back from V going this way, G, right? But let's suppose that we only take the image of G, just where it goes to. And that's actually a subset of our domain, R3. Now, what we get is we actually get an isomorphism between G of V and V. In other words, a right inverse, what it does is it takes the range, which is the full codomain for surjection, and it sends it right back into the domain so we can actually see it in the domain. And it's a subset of the domain, actually a subspace of the domain, that is isomorphic to the range itself. Okay, so with that, let's take a look and see um, what we can with this with a little image. So let's suppose that we are in the domain. So this is a picture of the domain like R3. Okay, I have some things drawn in here. What are they? See the green lines? The green lines are just instances or examples of fibers of a map or of a linear transformation. Now, the kernel, which is the fiber over 0, is a subspace. So only one of these lines is a subspace. It's the one that has 0 in it, line that goes to the origin. All the others are shifts of that, because for a linear transformation, all the non-empty fibers are simply shifts of the fiber over 0. Okay, so now what are fibers? Let's kind of remember. Think of a fiber box diagram. Let's think about that for a minute. So if we have a function, we can represent it by a fiber box diagram. That means we take all the elements of the codomain, and each one element of the codomain, say like A, B, C, has a box associated with it. This box is all the elements in the domain that are actually sent to that codomain element. All the elements that are sent to that codomain element. All the elements that are sent to that codomain element. Now, so if we're looking at this linear transformation in the fibers, each of these fibers, so each of these green lines is actually sent to just one codomain element. Okay, just one codomain element. Now, you notice also in the picture that I have this plane I drew that kind of intersects all these green lines. Why is that? Well, notice I drew a plane such that every point in the plane represents exactly one fiber, meaning that there's exactly one fiber that pierces that point in the plane. Now, there's infinitely many fibers. It fills the space here, but I only drew a few of them, okay? But it's going to intersect the plane in one place. So the plane actually itself is a representation of all the fibers. It's a one-to-one correspondence between all the fibers. Now, since it's a one-to-one correspondence between all these non-empty fibers that I've drawn, it's also a one-to-one correspondent in one-to-one correspondence or bijective correspondence with their labels, the labels of each fiber in the fiber box diagram. Those are just codomain elements. Now, since it's surjective, and these are non-empty, we've hit all our codomain elements. We've hit the whole range. So the range itself, which is the codomain of a surjective map, can actually be represented by this plane, but it's represented isomorphically. What we're doing is we're describing all the elements of the range in the domain itself. Now notice it's a subspace. This plane goes through the origin, and a plane is a subspace. This subspace is actually isomorphic to the range itself. So imagine having an isomorphism that goes from the range, which is the codomain, so V, right? And this isomorphism goes from V back to this plane. Okay, so that's G. That's what G is. G is going from this vector space V and going back to the plane. Now, what does the function do? So we're in the domain right now. So the function would naturally take everything and take it to V right here. Now, if we run G back, we actually will hit up where we hit. Like, let's suppose, see this fiber right here. What if we map right to where it intersects that line? So basically, everything in this fiber has the same image in V. So this whole thing is sent to the exact same thing over here in V by F, and G will send us right back into that particular fiber right there. That's what G does. G will send us back into the fiber of wherever of the codomain element that was over here. Now, of course, there are many different examples of right inverses that we could actually have here in this case. Many different examples. For instance, there's lots of different planes, right? We could draw a plane this way, or we could draw a plane that way, or whatever. We can draw lots of different planes that are subspaces, and the plane itself kind of gives us where we should be, where we're going to be sending elements back to. And there's lots of different ways, but no matter how we arrange it, we're still going to be getting into the same green line, okay? So if we came from a green line, we're going to go back into it. That's what a right inverse does. So it takes something on the green line, sends it to V, and then when you go back, it sends you to another point on the line. That's essentially what a right inverse does. So it keeps us in the same fiber if we start, so if we start in R3, we head over to V, and then when we go back, we're going to be in the same green line that we were to begin with. That's the functionality of a right inverse. Now, there are many different kinds of right inverses out there that we could potentially have. Here's just one quick example. Let's suppose that we have this particular, let's see. Let's suppose that we have, so here's our example. Let me get this right shape here for this matrix. So we're going to have, we're going to do R3 as the domain. All right, so R3 is the domain. And let's suppose it looks something like this. So we have 1, 0, 1, and then we have -2, 1, 0. Now there's two right inverses. If we multiply on the right, let's suppose we have something like this. 0, 0, 0, 1, 1, 0, and you can check it. If you multiply this to this, where this is on the right, you'll actually get the identity matrix. What does that mean? That means that if we do this map in the column interpretation first, and then that one, meaning that we've done G, then F, it'll be the identity, meaning we'll get back to the same location, like this. What does that mean? That means we had a codomain element, we got it over here, and then we map back to the same codomain element. Meaning that okay, that basically right here, we start here, we go into somewhere and back here. Now, if we were originally in the, so since this is a surjection, every element in here already has a pre-image, right? So, or it came from somewhere. So it came from somewhere, but it's going to come back to that same place, meaning we stayed in the same green line. So if we get the identity matrix, it's a 2 by 2 identity matrix, 1, 1, 0, 0, if we perform that multiplication. Now there's another one that actually does the same thing. And that one in particular, here's an example of that. If we have 1, 2, 0, and 0, 1, 0, this one also, if you check, if you do this matrix multiplication, will also give you the same identity matrix and has the same thing happening. So different right inverses can send us into or to different planes or different places. So it's just an example of that. Hope you enjoyed this little visualization, and thanks for watching.